All right, now this is a really fun example to work with. We're going to kind of undo a derivative, as it were. So what we're going to do is we want to find a function who has a derivative of the sine of x, but whose graph passes through the point 0, 2. So they've given us the derivative sine x, and they've given us the point 0, 2. Those are two key critical things that we're going to need to know. And so what we're going to do is we're just going to ask ourselves, all right, if the derivative of what is equal to sine x? The derivative of what is equal to sine x? And if you think about it, you know, if you look at like any study aids that you have, or if you remember, the derivative of the cosine is the sine. So that's important, okay? The derivative of what is sine x, okay? So derivative of cosine is negative sine. Well, how can I get this to work out where when I take the derivative of the cosine, I get a positive sign? You make cosine negative. So what we end up with is negative cosine x plus c. So we're going back up, okay? We're anti-differentiating, and you see that right here defined underneath. So what happens next? Well, just double check yourself. Is the derivative of negative cosine x sine x? I think it is. So we're good to go. And then what we're going to do is we're going to use these values where x is equal to 0 and y is equal to 2, and we're going to plug them into our equation. And when we do that, we solve for c. So we're going to have f of x equals negative cosine x plus c, all right? And what we're going to do is we're going to substitute in 2 for y and 0 for x. So go ahead and fill in those things and then solve this for c. So the cosine of 0 is 1, so I'm putting a negative in front of that. That's negative 1. And then y value is 2, so I have 2 equals negative 1 plus c. When I do that, I end up with c being equal to 3. So this then gives me my function, my original function of negative cosine x plus c, which is 3. Okay? That's how it works. Pretty cool, pretty cool. And don't forget plus c. That plus c part is key to the whole situation. All right. Now down here, the antiderivative, a function capital F of x is an antiderivative of a function little f of x if capital F prime is equal to f for every x in the domain of the function. The process of finding the antiderivative is called antidifferentiation. Another word for antidifferentiation is integration, and we will spend the whole second semester talking about that. But this is just a little glimmer into what we're discussing here. So if f of x is x cubed, then capital F prime of x would be 3x squared. Okay, notice the relation here. If I started down here with the f prime of x, when I find the antiderivative of it, I just go, okay, the derivative of what is 3x squared? And we have to think just a little bit, but it's not a hard thinking. Like, you know, if we've got x squared and it's a derivative, I had to have an x cubed. Now how do I get that 3 to go away and just become a 1? And you know, how does all that work? Well, it'll take a little bit of practice, but if you'll just notice some relationships right here, okay? I increase my exponent by 1. I go from 2 to 3, and then if you'll notice, I just divided by the 3 divided by 3, and that gives me 1. Okay, and so to really have the good antiderivative here, we need to make sure and add plus c. Why? Because I can put several different constants over there and get the exact same derivative every single time. So we need to recognize that there's a whole family of equations that go into this problem that when I take the derivative of them give me 3x squared. So that's how anti-differentiation works, and again, we're going to spend a lot of time talking about all kinds of different ways to use the antiderivative.